Hello, and welcome to another episode of the Math Club podcast.
Hang on just a second, Pete. What is that?
Whatever it is, it ain't local.
Well, that happens to be one of my favorite clips from one of my favorite movies of all time, Contact.
Oh, yeah, Contact. Definitely one of my favorite movies, too. And I also love that scene.
Yeah, well, in that clip, Ellie and her team, which are part of SETI, the Search for Extraterrestrial Intelligence, have just received a signal that is enumerating prime numbers, starting from 2 and making its way up to 101.
Right. The signal that they hear is pulsing, and it pulses twice, then it pulses 3 times, then 5 times, then 7, and Ellie notices
primes. 2, 3, 5, 7. Those are all prime numbers.
And I have to tell you, every time I watch that scene or even just think about it, I get this kind of shivery feeling because I think, oh, I know prime numbers. Those are like near and dear to my heart. And the idea that this would be part of that first contact, that first transmission is, it's exhilarating. Today's episode number 4, Prime Time. I'm one of your hosts, Pete Littig. I'm a software engineer and a former math professor.
And I'm your other host, Noah King. I'm an elementary school teacher who's been teaching for almost 30 years, and I love math.
So, Pete,
why do you think Carl Sagan imagined aliens communicating using prime numbers? Why did he think that might be a reasonable strategy for the aliens to use?
Well, if you remember from the movie, and I went and looked this up, one of the first things that Ellie says is, there's no way that's a natural phenomenon. And I agree. If you received a signal of prime numbers, you would not think, oh, that's just some quasar doing its quasar thing. Like, some intelligence has to be behind that. But it's also not unfathomable, right? This is what I think is going on. There's a bridge between, on the one hand, counting, which is a very simple, basic, let's go ahead and say natural human process.
1, 2, 3.
And that bridge connects to a much more complex world, which is to say the world of abstract mathematical structure. Prime numbers are this complex pattern that requires some form of intelligence to perceive. So I think there's a neat way that aliens might, try to connect like the natural with the abstract in this way.
So it's kind of a way for them to signal, hey, we're here. This isn't just some randomly occurring natural phenomenon. Pay attention to this.
Yeah, and at the same time, it's not so far advanced that we have no hope of grasping it.
That's interesting. So let's take a step back and go over some definitions before we get any further in our episode, Pete. So
sure, yeah.
For people who may not know, what is a prime number?
Yeah, a prime number is a positive integer greater than 1 that is divisible only by 1 and itself.
So, okay, well, I want to stop you because I've always had a question about that definition. Why do they have to specifically exclude 1? Like it's not allowed in the prime club. Like 1 is trying to sneak on in and the bouncers come up and go, hey, 1,
right. Yeah,
get out of here.
You're out of
here. We said any positive integer greater than 1. Why can't 1 be prime? 1 is only divisible by 1 in itself, right?
Yeah, and one way to address that is with just kind of a shifty dodge and to say, well, how about this? Let's define a prime number as any positive integer that has exactly 2 distinct divisors. And now we have also ruled 1 out. But somehow I think that's not exactly what you're getting at. I think you want something with a little more substance, like what is the actual reason?
Well, is there a reason that it would be difficult for some operations that we use primes for if 1 were allowed in the club?
Yeah, well, probably the most convincing argument for ruling 1 out is the fundamental theorem of arithmetic, which states that...
Wait, hang on one second. There is something called the fundamental theorem of arithmetic?
Oh, every elementary school teacher knows.
Well, I was about to say, I've been teaching elementary school for almost 30 years, and I have never heard of or taught something called the fundamental theorem of arithmetic. So please enlighten me on what I've been missing here all these years.
You should listen to our podcasts after we're done with them, because I think you will learn something. Yeah. So here's what the fundamental theorem of arithmetic says. It's maybe a fancy way of stating a very familiar fact, namely this: every positive integer greater than 1 can be uniquely expressed as a product of prime numbers.
Okay, so give an example.
Sure. Let's take the number 168. Okay. So if I asked you to factor that, what would you do?
Well, first I would divide it in half, and I would say that's 2 times 84.
Right.
And then I would divide 84 in half again, so I would say it's 2 times 2 times 42. And that's 2 times 2 times 6 times 7. All right, so I've got a 2, and a 7 are all prime, but I've got a 6 there, which is, so it's 2 times 2 times 2 times 3 times 7. So basically, I guess what I just did is I figured out the prime factorization of 168.
You did. And now I want to say it back to you in a very particular way. 2 cubed times 3 times 7. So that is a representation of the number 168 expressed using only prime numbers. And we've arranged it so that the prime numbers themselves are in increasing order. First, I tell you about the 2s. Then I tell you about 3. There's no 5, so I go on to 7, and now I'm done. So 2 cubed times 3 times 7. Every positive integer can be factored in this way, and it is unique. The result is unique.
So is that the same thing as saying every positive integer has some sort of prime factorization that you can continue to factor it down until you get down to just the primes that make it up?
Yeah, exactly. And I do want to call attention again to the importance of the uniqueness. In fact, this is an example of a very common type of mathematical theorem, namely an existence and uniqueness theorem. It says something exists, a prime factorization, and it is unique. As long as we group the like terms together and arrange the primes in increasing order, we have a unique factorization.
Okay.
Right. Somebody could have said, no, it's 3 times 2 times 7 times 2 times 2. Like, sure, it is, but let's make that
changing the order.
That's just changing the order. Exactly.
Okay, so I understand the fundamental theorem of arithmetic, but you were using it as an example of why we can't include 1 in the prime club. So how do we get to that?
Right. And it isn't so much a reason as to why we can't include 1 in the prime club, but it's a good reason why we might not. For example, let's take a smaller number. Let's take the number 18. I could write 18 as 1 times 1 times 1 times 1 times 1 times 1 times 2 times 3 squared. And all of those ones that I put out front convey absolutely no information about the number 18. What's important is the factor of 2 and the factor of 3 squared. So because we can just continue to stack ones up till the cows come home, it just muddies the statement of the theorem. The theorem no longer has that sort of crisp feeling about it.
I see. Just like when we take the prime factorization of a number, we don't just add a bunch of branches with 1s at the end of them.
Yeah, exactly. Exactly. And so I should say this is really a convention that emerged over time. In fact, going back to the middle of the 18th century, sometime around 1740, 1750, mathematicians like Euler and Goldbach were occasionally making reference to 1 being a prime number. And they would always have to say, except of course, what, always had to make some, like, we have to rule this out. And then at some point, definitely by the time of Gauss, people were much less likely, I think, to throw 1 in as a prime. Okay. So Gauss, of course, is famous for many, many contributions to mathematics, especially number theory. In fact, I believe it was Gauss who said, if mathematics is the queen of the sciences, then number theory is the queen of mathematics. Gauss is really the first one to formally write down a proof in modern terminology of the fundamental theorem of arithmetic.
Well, here's another question, and I think I've got enough now that I can answer my own question, but let me ask it. What about negative numbers, like -3? Can -3 be a prime number because its factors are 1 and itself, -3 and 1, but it also has the factors of 3 and -1, doesn't it?
It does. And
so does that exclude it from being prime?
Well, again, this is essentially a convention and a matter of choice. Usually the notion of prime number is reserved for positive numbers that are greater than or equal to 2. There are certain algebraic settings, like I'm thinking ring theory and algebraic number theory, where we talk about primes all the time, and they're not just numbers, they're now elements of a ring. And in that setting, we would think of -3 as being a prime. But for the sake of your everyday conversation about prime numbers, I think we ought to stick to the positives.
Yeah, I'll tell you, if I was 1 and I saw -3 getting let into the club, I'd be saying something. So is there any kind of pattern or rhyme or reason to the distribution of primes in the number line? Like can you look at the first 10 or 15 primes and sort of from that deduce a pattern of what the next set of primes are going to be?
If only. Not that anyone has been able to determine. Of course, people have been looking for this for a very long time, probably going back to the time of the ancient Greeks. Euclid was right.
Those guys again.
They're inescapable. All roads lead to... Wait, Rome's not in Greece. Is Rome?
No, Rome is not in Greece. I think you need to brush up on your fundamental theory of geography.
I do. I need to find a history club podcast. So Euclid wrote extensively about prime numbers in his series of books, The Elements. He actually proposed some definitions for primality. He talked about the infinitude of primes. He really sort of laid a lot of the very basic material down. And we have been wondering ever since, okay, but how do we continue to find them? There are infinitely many of them. Where do we find them? How are they distributed? And we only have the beginnings of understandings around that.
So you mentioned Euclid. I seem to recall from high school that there was an important proof that Euclid made around primes, but I don't remember exactly what it was or what the details are. Do you know what I'm talking about?
Oh, I do. And this is fantastic because I think there are 2 proofs that everyone who goes through high school ought to know. And you obviously didn't learn this one that we're about to talk about, but that's okay because we'll take
it was a long time ago.
It was, admittedly. Euclid's proof that there are infinitely many primes. It's really a classic example of what we know as a proof by contradiction. Let me ask you this question, Noah, before we dive into it. If you were tasked with showing that there are infinitely many primes, how would you go about it?
Well, I guess I would start. I was going to say I would start listing them, but at no point would I get to a spot on that list that would prove there were infinitely many. Because I would never have a list that was infinitely long, would I?
No, definitely you wouldn't.
I guess I would try to prove that there's no reason to think that any particular prime is the largest prime.
Yes, and I think that's a great intuition. And I think that what we can do is sort of use that to leap into Euclid's proof by contradiction. And so just as you say, there's no reason to believe that some particular prime is the largest of the primes, Euclid starts by saying, let's suppose there are only finitely many primes. So we can write down a list of all of these primes. Let's call them P1, P2, all the way up through Pn. I'm just using P for prime, and N is the final one. Whatever that final one is, we're saying that there are N of them.
Okay.
And now we're going to do something kind of clever. We're going to use these primes to make a new number. I'm going to call that number A, and I'm going to set it equal to the product of all of these primes, and I'm going to add 1. So A is equal to P1 times P2 times ... All
right. So if my list just had the first 3 or 4 primes, if it just had 2, 3, 5, 7, I would then multiply those together. So 2 times 3 is 6, times 5 is 30, times 7 is 210, and then I'm going to add 1 more, so I'm going to get 211.
You are, exactly. Now, what's interesting about that example you just described is that 211 is prime. So if we thought we had all of them, what we just did is we produced another one. So nope, our list was incomplete. We were wrong. However, this process does not always generate a new prime. It may seem like it because if you started with 2, 3, 5, 7, but if you do 2, 3, 5, 2 times 3 times 5 is 30, plus 1 is 31. That's prime. 2 times 3 is 6, plus 1 is 7. That's also prime. You may think, I will always get a prime. You don't. When you go
If
up,
I just use 3 and 5 on my list, if I just do 3 times 5 is 15 and add 1 and I get 16, that's not prime.
exactly. And in fact, if you do the primes 2 through 13 and then add 1, I believe you get 30,031, which is not prime. But we'll let listeners have some fun checking that on their own. But that's actually not what Euclid had to do. His proof does not rely on this number somehow being prime. In fact, what he says is this number must be composite because our list P1 through Pn was comprehensive. We had already assumed that every number that's prime was on our list. This number, A, is bigger than any one of those individual primes, so it can't be one of those primes. It's too big. Therefore, it must be composite. Now, because it is a composite number, it is divisible by a prime. One of those numbers on our list, P1 through Pn, will divide into A. And this is the foundation for the contradiction.
So what you mean is that if I take this comprehensive list of primes and multiply them all together, I'm going to get a number that's divisible by all of those primes. But then when I add one more, now I'm going to get a number that's not divisible by any of those primes. Because, for example, 7, I would have had to have added at least 7 more to get to the next multiple of 7. I only added 1 more. Same thing with 5. Same thing with 13. Am I kind of following where you're going of why that number is not going to be divisible by any of these primes and is therefore prime itself?
That's the intuition behind it. Exactly.
Okay, so we've determined that there isn't such a thing as the largest prime, period. But I'll bet there is such a thing as the largest prime that's been discovered to date. And I wonder what that number is.
There is. And you asked earlier about patterns and about distribution of primes. I think there's a lot of interesting things we could talk about in a later episode around the prime number theorem, which addresses exactly that question. But because we don't have a way to produce prime numbers with certainty, we do have some biggest one that we know about. And in this particular case, it has a very fussy name. This biggest one was discovered in 2018, and you'll see what I mean here. Its name is M8258993.
And so wait, this number has a name that's another number?
It's yes. And
have you met number 7? Its name is 52.
Well, there's a reason for this madness. So first of all, let me tell you, the number has more than 24 million digits. In fact, it has exactly 24,862,048 digits. I want to see the cast of Rent sing a song about 24,862,048 digits. Yeah, I think that would be amazing. So now the reason it's named M8258993, the M stands for Mersenne, a French intellectual Catholic priest named Marin Mersenne, born in, I believe, 1588. And he was at the hub of a lot of intellectual life back then, including, he was friends with Descartes. He certainly knew Fermat or was very well aware of Fermat. And among his many intellectual pursuits was the study of mathematics. And he was interested in prime numbers that could be written in the form 2 to the n minus 1. In other words, prime numbers that were 1 less than a power of 2. Now, you already know some of them. For example, 3 is a prime number that is 1 less than a power of 2.
Mm-hmm.
It's 4 minus 1. 7 is 8 minus 1. 31 is 32 minus 1. So these are examples of Mersenne primes.
We skipped one because it's not prime. So 16 minus 1 gives us 15.
That's right.
Which is not a Mersenne prime.
It is not. It is a Mersenne number, but it is not a Mersenne prime.
Gotcha. Now,
the notation M8258993 tells us that if I take the number 2 and raise it to the power 82,589,933 and then subtract 1, I do get a prime number, and this is the one we're talking about.
Okay.
And so here's something that's interesting. Mersenne was studying these numbers back in the early 1600s. We still don't know if there are infinitely many of them, Mersenne primes. Since he first introduced this idea, we have found exactly 51 of them. How many are there? We don't know.
You know what this reminds me of? This is actually going to be more meaningful to people who heard our previous episode about Pythagorean triples. But remember when you decided to try to find more Pythagorean triples, you created a series of steps that would yield other Pythagorean triples.
Yeah.
It almost seems like this is a way that Mersenne figured out to search for and find possible primes that hadn't
Exactly.
been found yet in a similar way. It doesn't always yield a prime result, but it does work sometimes to find primes.
It does. And you're absolutely right. In fact, here's something interesting. If the number 2 to the n minus 1 is prime, then the exponent n must also be prime. So that reduces your search space. Already we know you only need to check 2 to the power of a prime and then subtract 1. The reason the biggest known prime number of all time is a Mersenne prime is because it's a technique that we can exploit to try and find more primes. Otherwise, what are you going to do? Just get hey, big numbers, come here. I'm going to check you out. Like there has to be some structure that we pursue to find these big primes. And this is one of them.
So are there other kind of unsolved questions centered around the idea of prime numbers?
Yeah, there's a treasure trove of them. If we go back to our opening where I was sort of pontificating on this beautiful bridge connecting the simplicity of counting with the structure of prime numbers. And that's something you can think about if you're an elementary school student. You can think about prime numbers. We have loads of open questions in mathematics that involve prime numbers. For example, the infinitude of Mersenne primes. That's one that we just talked about. It's unknown if there are infinitely many. Here's another one. There's something called the twin prime conjecture. So some primes come in sort of, let's call them twin pairs. So 3 and 5, for example, 2 prime numbers. They're separated by a distance of 2, 3 and 5. Obviously, the number in between them is even, so it couldn't be prime. But 5 and 7 is another such example.
11 and 13.
Exactly. How many of those are there? We don't know. The conjecture says there are infinitely many of them, but we don't know.
And that couldn't that be proven in the same way that Euclid proved that there was no largest prime?
Like a proof by contradiction let's assume there's a whole.
Yeah.
Well, if there is one, nobody has found it yet. Here's another related problem. And this goes back to Goldbach. In 1742, he formulated a conjecture that says every even integer greater than or equal to 4 can be expressed as the sum of 2 prime numbers. So think about that for a second.
So like 4 can be expressed as the sum of 2 and 2.
Yep.
And 6 can be the sum of 3 and 3.
And let's try one a little further along. 24 is 11 plus 13.
Oh, wow. That's
50
that's interesting.
Is 3 plus 47. And in fact, many even numbers can be expressed as the sum of 2 primes in lots and lots of different ways. But yet, we don't know. Is this true for all even integers? We don't know. It's an open conjecture. And you see what I mean, Noah? This is something you could take a class of 5th graders. You would know better than me, but you could take a class of 5th graders and explain this little conjecture, and they could start thinking about it. They could play around with it.
That's not beyond their ability to start thrashing about with it and seeing what they can come up with.
Exactly. And this is the allure of primes, right? I like to think of them as the building blocks of the integers, which of course is where we do all of our basic arithmetic. And there's this allure. We have these problems that are easy enough to state that, elementary school students can start working on them, and we just don't have the answers yet.
Yeah. Okay, so circling all the way back to where we started with the movie Contact.
Yeah.
So are prime numbers used for communication like that?
Only with aliens, it turns out. Otherwise, the answer is actually yes, in a less direct way. And I think we should talk about that in another episode, because I'm going to guess you have purchased something online using a credit card. Is that right?
I think I see where you're going. A lot of the things I purchase online, I purchase from Amazon Prime.
No.
Is that where we're going with this?
That sounds just about wrong.
Okay, sorry. Go ahead. What were you going to say?
But everything that you purchase through, for example, Amazon or any other site where you need to maintain security, there is a cryptographic algorithm which is protecting your credit card number, and it is based on prime numbers. So that's something that we can take up in a new episode.
Sounds great. This has been a very interesting conversation about primes. Pete, why don't you tell our listeners how they can get in touch with us if they have any questions or suggestions for future episode topics?
Absolutely. I would be delighted for any of our listeners to reach out to us. You can find us in two places. Our Twitter handle is @MathClubPodcast. And our Gmail address is mathclubpodcast@gmail.com.
Thank you, everybody, for listening, and we will see you next time.
Take it easy.